Chapter 12, Sampling and the Big Picture. The model has handed us a probability for every possible next word. Now we make the final choice and then watch the whole machine run. Let's finish this. So we have our distribution, mat 60%, floor 20%, and a long tail of others. How do we pick just one word? It turns out this choice has a big effect on how the text feels, whether it is safe and repetitive or surprising and alive. There are a few strategies, let's meet them. The simplest is greedy decoding. Always take the single most likely word. Matt wins every time. It sounds sensible, and for short factual answers it often is. But used for long text, greedy decoding tends to get dull and repetitive. The model keeps falling into the same safe grooves. So instead, we sample. We roll a weighted die. The word with 60% is picked about 60% of the time, but sometimes a less likely word gets its turn. This brings variety and surprise. The trouble is, way out in the tail, there are thousands of terrible words, and we don't want to ever pick those. The fix is to trim the tail. Top K sampling keeps only the K most likely words, say the top 40, throws the rest away, and samples from just those. We renormalize those few back to 100% and roll the die among them. Good words stay in the running, the garbage is cut. An even smarter version is top P, also called nucleus sampling. Instead of a fixed count, we keep just enough of the top words for their probability to add up to, say, 90%. When the model is confident, that might be only 2 or 3 words. When it is unsure, it might be many. The size of the shortlist adapts to the model's own certainty. And now, the moment it all comes together. We pick a word, we append it to the text. Then we feed the whole thing back in, and the entire model runs again to predict the next word. Token by token, the sentence grows. This is the autoregressive loop from Chapter 1, and now you know exactly what happens inside every single step. Let's stand back and see everything at once. Text becomes tokens, tokens become embeddings, we add position. Then many times over, attention lets words share, and the feed-forward network lets each one think. The final vector becomes logits, softmax and temperature make probabilities. We sample a token and loop. That from beginning to end is a large language model. And that is the whole machine. Not magic, not a mind. Just tokenization, vectors, attention, and a great deal of learned arithmetic, trained to do one humble thing, predict the next word, at a scale that becomes something remarkable. You now understand end to end how a language model works. Thank you for building it with me.